Hello students, welcome back. So today we are going to discuss and understand these kind of questions from the chapter Alkyl Halides. That is, list the following alkyl halides in decreasing order of Sn1 reactivity. Three alkyl halides are given here. First, 2-bromo-2-methyl-butane. Second, 1-bromopentane. And third is 2-bromopentane. We have to identify which among these three is more reactive as far as Sn1 reaction is concerned. And then we have to propose the mechanism of most active compound from above with aqueous KOH. So whichever among these three is most reactive for Sn1, that compound, either 1 or 2 or 3, that we have to identify first. And this compound, the most reactive among these three, we have to treat with aqueous KOH and we have to predict the product. And for such type of question, the mechanism is important. Means if it is Sn1, what is the mechanism of reaction? If it is Sn2 reaction, what is the mechanism of reaction? Okay, so to understand these type of questions, we first have to understand nucleophilic aliphatic substitutions. That is, we have to understand basics of Sn1 and Sn2 reactions. So let us start with today's session. Nucleophilic substitutions, these are characteristics of alkyl halides. We denote alkyl halides by Rx, where R represents alkyl and X represents the halide. This is because of its functional group halogen. The halogen which is present, that is more responsible for these nucleophilic substitution reactions of alkyl halides. Nucleophile means the nucleophilic reagent, which we denote by Nu-. This nucleophilic reagent is basic, it is electron-rich reagent, and it tends to attack the nucleus of carbon. That means the positive. Okay, the electron-rich reagent that tends to attack the nucleus of carbon. Rx, that is alkyl halide. Okay, nucleophile will be attacking this Rx. We all know that this halogen has the lone pair of electrons on it, right? So nucleophile will tend to attack here, and the nucleophile will get substituted here, and X minus will go out of the molecule. Okay, so in place of X, we can see here, in place of X, Nu has come, that is nucleophile has come. So we call this a substitution reaction. Which substitution? Nucleophilic substitution reactions. So these nucleophilic substitution reactions are of two types, that is Sn1 and Sn2 reactions. Sn1 is unimolecular type of reaction and Sn2 is nothing but bimolecular reaction. Now, before we proceed, you must have seen this particular image quite number of times on on the internet. But again, using the same image, I will try to explain what is Sn1 and Sn2 reaction. You can see here the small cat is looking at this cat, right? So this big fat cat is sleeping nicely in the bed. So let me call this as R and this is X. So this Rx bond is already made here. Okay, this Rx is available here, and this small cat, let me represent it as nucleophile. Now this nucleophile wants to come here and sleep. See here, first image exactly same. This is R and X, and this nucleophile is looking at the sleeping cat in the bed. Let us look at this last image where this X has come out and now R has made bond with this nucleophile. Same way, this last image also, R has made bond with nucleophile and X has come out over here. So can we see that the first image and third image in both the rows, they are same. That means what? That means reactants and products both are same, right? So whatever happening in between, that is different. Okay, and that difference in mechanism causes this Sn1 and Sn2. Okay, so let me tell you here R and this X bond is breaking, right? R and X bond is breaking over here. Okay, this bond is breaking. Still, this nucleophile has not come. So unless and until X is completely gone, nucleophile will not come here, right? And in Sn2, the second row here, R, this big fat black cat is not going, no? So this yellow cat is trying to push out the black cat, right? So this bond is breaking over here and this bond is getting formed at the same time, right? So this is the difference between Sn1 and Sn2 reactions. The difference lies here. Okay, here the bond will first break between R and X and then nucleophile will come here and attach. But here in Sn2, the bond of R is breaking with X and it is forming with nucleophile simultaneously. Let us understand more about this. The RX alkyl halide, this arrow I'm showing like this because it's a slow step. You saw, no? The cat was initially not getting up from the bed. The other cat is waiting since long. It's a slow step. And now here the R and X bond is first broken and then hence it is R plus and X minus form. So we call this R plus as carbocation. Whenever there is carbocation, there is possibility of rearrangement. Possibility of rearrangement. Why? Because tertiary carbocation is more stable than secondary and secondary carbocation is more stable than primary. So that means if primary carbocation is formed here, we should look for the changes to make it secondary or tertiary because of its stability, of course. Okay. So this is called as step 1. Let me call this as step 1. Okay, where this carbocation is formed. Now the second step, where the carbocation is reacting with this nucleophile and R and U bond is formed. So this is called as step 2. Okay, this is step 2. So I hope this is clear. In Sn1, since the bond is first broken, there is formation of carbocation. If I see carbocation, I have to look for the possibilities of rearrangement. About this rearrangement, we also had a small discussion in the previous video. That is, I think, part 3 or part 2 of alkyl halides. Okay, and then once the carbocation is formed, nucleophile here can attack the carbocation so that the RNU, nucleophilic substitution, is happening. Some of the important points to remember from the Sn1 reaction, that it's two-step reaction. Yes, we have seen that. Carbocation formation. And here rate of reaction is directly proportional to the alkyl halide. Okay. And see this alkyl halide to the concentration of alkyl halide here, I mean to say. So this step 1 which was there, no, where we have written slow step, that is rate determining step. Whichever step is slow step in the reaction, that is called as rate determining step. And here the rate of reaction doesn't depend on nucleophile, but it depends on the alkyl halide, and thus the molecularity of the reaction is 1. So what is molecularity here? Number of molecules involved in the rate determining step. So in rate determining step, what is involved? Only the alkyl halide. How much time it is taking to break the alkyl halide. And reaction follows first order kinetics here. Hence the order of reaction is 1. The rate of reaction of Rx is based on stability of respective carbocation formed. I told you this point earlier also. So tertiary carbocation is preferred over secondary and secondary is preferred over primary. That means what? tertiary carbocation is more stable than secondary. Secondary is more stable than primary. So if you're forming the carbocation, if the carbocation is formed, it will try to get converted to more stable form. Now next, the rate of reaction of Rx based on halide. So whether that X is iodine, bromine, chlorine or fluorine. So based on that, the stability of the alkyl halide or the rate of reaction of alkyl halide is Ri is more reactive than RBr. The bond which is broken easily will make the carbocation easily and faster. So Ri bond here breaks easily among all. This is because the size difference of the atoms involved in the bond formation. So if it is fluorine, chlorine, bromine, iodine, okay, so iodine size is more than bromine, than chlorine and than fluorine. So Ri much of the size difference, and thus the living ability of this I is more. So we say that iodine is a good living group, okay, because of its lesser bond dissociation energy, hence more leaving ability. So this bond dissociation energy depends on the size difference. Nucleophile can attack the carbon substrate both from front and backside. The reaction is favored by weak or strong nucleophiles. This Sn1 reaction is favored by any of the nucleophile, which could be weak or strong. Okay, but the very important point here is the formation of carbocation. Which carbocation is getting formed here? If it is tertiary carbocation getting formed, then even the weak nucleophile can carry out or can undergo the Sn1 reaction. It is catalyzed by Lewis acids like silver chloride, zinc chloride, and so on. Sn2 reaction. Similarly, I have this alkyl halide with me. We have seen that the bond is not breaking here, right? Bond of Rx is not breaking so easily, but this nucleophile wants to come here and it will attach to R. Now see here, there is negative charge over here. There could be lone pair of electrons here, lone pairs of electrons here also. So they try to repel each other, and therefore this nucleophile attacks are from backside. So we say that it's a backside attack of nucleophile. So this nucleophile has attacked alkyl group from backside, and on the front this halide is there. Okay, this is halide with so many lone pair of electrons. So delta negative region here, delta negative region here also. So relatively this particular region is positive. So this bond is getting formed and this bond is breaking. So we can say that this is bond breaking and here bond forming happening simultaneously. Okay, and this particular stage is called as transition state. Okay, and mind it, transition state is not considered as step, right? So next here completely this bond has broken and this bond has formed. So this is the product, exactly same product as that of Sn1 reaction, right? So here see the reactant products, and this was transition state in between. I told you transition state is not considered as the step. So there is only one step in this Sn2 reaction, right? So let us see some important points of Sn2 reaction. This is only one step reaction. There is formation of transition state. Rate of reaction depends on nucleophile as well as alkyl halide, right? Nucleophile is attacking from the backside because this X is not leaving, right? And therefore, rate of reaction depends on both. Hence, molecularity is 2. Reaction follows second order kinetics, and hence order of reaction is 2. Here, rate of reaction of Rx is exactly opposite as that of the Sn1 reaction. You can see here the tertiary alkyl halides are least reactive. I mean, they do not uh, undergo Sn2 reaction, and secondary are more reactive than tertiary, and primary are more reactive than secondary. Why is that so? Because see here, if I give you this example of CH3X, CH3, CHX, CH3, and let me take this tertiary CH3, CH3, CH3X. Okay, so see, this is primary alkyl halide, secondary alkyl halide, and tertiary alkyl halide. Okay, so the carbon, this is tertiary, this is secondary carbon, and this is primary carbon where this X is attached, right? And this nucleophile which is coming over here, that nucleophile is attacking from the backside, right? If this nucleophile has to come here, it will face more crowd. Here again, more crowded. Tertiary is more crowded. Thus, backside attack will be little difficult for the nucleophile, right? So, if it is tertiary or secondary alkyl halide, we need stronger nucleophiles. But if it is primary alkyl halide, even the weaker nucleophiles will be able to sometimes give the reaction. Okay, so what we have to understand here, the lesser steric hindrance here, lesser steric hindrance, and therefore the nucleophile can attack easily as it is less crowded. Okay, and therefore primary alkyl halides are more reactive as far as the Sn2 reactions are concerned. Okay, so let us move further. The rate of reaction of Rx based on halide, it will remain same, no? Because we are just checking here the effect of the leaving ability. They have to leave, right? Halide has to leave, and at this place, the nucleophile is going to come. So the one which has more leaving ability, okay, that will be more reactive. So effect of leaving ability of halide will matter in the same way as that of Sn1 reaction, and thus this point is exactly same as Sn1. Okay, because I is best among these halides. This is the best leaving group. Nucleophile can attack the carbon substrate from backside here. Okay, so there is backside attack over here. Reason we have seen on the earlier slides. The reaction is favored by strong nucleophiles. Usually the stronger nucleophiles, they give or they undergo the Sn2 reaction. Okay, but the nucleophile being strong or being weaker doesn't give the only reason for Sn1 or Sn2 reaction. It depends on the nature of alkyl halide, whether it is tertiary, secondary, or primary. No catalyst is required here, unlike Sn1 reaction, where in Sn1 reaction we have seen that some catalysts are required. So some of the examples of nucleophiles I would like to give here. Stronger nucleophiles, for the stronger nucleophiles which I told you, which give maximum time Sn2 reactions, and weaker nucleophiles which maximum time give Sn1 reaction. But we don't have to by heart this. Why? Because along with this, we have to check whether this alkyl halide is primary, secondary, or tertiary. So if it is the Sn2 reaction, then the primary is more reactive than secondary and tertiary. If it is Sn1 reaction, the tertiary is more reactive than secondary and then primary. Okay, so this has to be our priority, and then we will see the strength of nucleophile, whether it is stronger or weaker. Okay, so which are the stronger nucleophiles which undergo Sn2 reaction? Very easy way to remember this, the ones which directly have negative charge on them. For example, the OH minus. Okay, this OH minus I can get from KOH. Okay, where I have this existing as K plus OH minus. I may have reagent as alkoxide, okay, sodium alkoxide, where it is Na plus OR minus, okay. So here OR minus, this could be the stronger nucleophile. Then sodium iodide, again very good example, Na plus I minus, where I minus is a good example again. Then I have this K plus Cn minus, okay, where the nucleophile is this. This carbon has the lone pair here. So the attachment will happen with the alkyl part through this carbon and not the nitrogen. Okay. So very important in comparison to this is this AgCN, where the very important, huh? Why? Because this is not existing. You can call this as exception also, because this doesn't exist as the in the ionic form. This has the covalent bonding, right? So this AgCN exists like this, and this lone pair is on the nitrogen here. So if this is the nucleophile, then the attachment will be through nitrogen, unlike KCN. If KCN is the reagent providing CN, then the attachment will be through carbon. If AgCN is the reagent which is providing CN, then attachment will be through nitrogen. We will see one example of this type of this difference, okay, in next video maybe. Next reagent could be KNO2, where K plus NO2 minus, where this NO2 can exist in this way. So the attachment will be through oxygen. Again, one more exception here, AgNO2, okay, where again covalent bonding, and this exists in this way. So the attachment will be through nitrogen here, this nitrogen. Here the attachment will be through oxygen. Few more examples of the stronger nucleophiles again. So this is maybe they are COO minus Ag plus. So here RCOO minus will be the nucleophile. Then we may have the lithium aluminium hydride as the reagent providing H minus as nucleophile. We may have the metals also, where this alkyl group, okay, R minus is available as nucleophile. So these are some of the examples of the, let me just remove this from here. Okay. So some of the examples of the stronger nucleophiles which can easily undergo Sn2 reactions. Okay, these are nucleophiles, examples of nucleophiles. But just looking at the reagent, we cannot decide whether it will be a Sn2 reaction. For that, we have to pay attention to the primary, secondary, or tertiary nature of the alkyl halide. Okay, if you see some of the weaker nucleophiles which undergo Sn1 reaction, again, the neutral molecules. Okay, neutral molecules and weaker like water. Okay, then NH3, NH2, and I also can have this NH. But see, these are quite stronger. These are quite stronger than the water. Okay, they're stronger than water, far, far stronger than water. So it is possible for this to undergo the Sn2 reaction if the primary alkyl halide is there. Okay, I hope this particular concept is clear with you. And now this particular question, the following alkyl halides in decreasing order of Sn1 reactivity. So for that, let me first write the structure of each. And they have asked us the Sn1 reactivity. So who is more reactive in Sn1? We have just now seen tertiary is more reactive than secondary than primary. So we can say that A is more reactive as far as Sn1 is concerned, then C and then B. Okay. For this is their Sn1 reactivity. So if this is my most active compound, I have to show its reaction with this aqueous KOH. So let us see that on the next slide. Sn1. So tertiary is more reactive over here, and the reagent which is given is aqueous KOH. Okay. So you may say that aqueous KOH, madam, you have just now said that it is stronger nucleophile and it will give the Sn2 reaction. But I told you that this is tertiary. So the product is going to be same, whether it is Sn1 or Sn2, the product will be same. But the in between mechanism we are talking about here, that will be the first preference you have to give for the nature of alkyl halide. Okay, since it is tertiary, okay, the easiest way for this particular reactant to form the product is through Sn1. Okay, so what will happen over here? The carbocation will form. Okay, we have to show in answer sheet the formation of carbocation. Why? Because we are showing the Sn1 reaction over here. Okay, and then this K plus OH minus will come in the picture. Okay, it will come here, and this will be the product. Okay, I hope this is clear. And some of the examples of Sn1 and Sn2 reactions, identifying it as well as showing the reaction mechanism, that we will see in the next session.